doing this over here. For these probability rules, the part of the trick is to not overthink it. When we're looking at this setup, it's kind of like, have you ever been in one of the stores where it's like this spinner that you say, hey, spin it, whatever you get, that's your discount for today. Some of us have seen that before, yeah. Or sometimes they even have that now in emails where, here, click on this and it'll see what your discount is. Those aren't rigged or anything. Please. We want to find out the probability that a customer gets more than a 20% discount. So which discounts qualify? The 30 and 50. Those are the only ones. How many customers are we putting through for this one question? Just one customer. So that one customer, how many different ways can it get a more than 20% discount? 3. So 3 out of, boom. Yeah, I don't expect to see this where it's 2/10 plus 1/10. But I do need to see 3/10. Okay, because that fraction is your work for this. What you want out of what's possible. Problem 2 says a customer gets less than a 20% discount. So how many options are there for that? 5. There are exactly 5 out of the 10, or 0.5. Okay? So far, so good? One person, very easy to work the probabilities. Now it's saying, what is the probability the first 2 customers both get a 50% discount? The rules that we have so far rely on whether or not things are disjoint, which is the same thing as mutually exclusive, or whether or not they're independent. And since for this one we're taking one person and then another, we're looking for that independence. So is one person's winning going to affect the next person's winning or discount or whatever? No, technically it's supposed to reset itself. So because they are independent, we should be able to just use our multiplication rule. How many of them are possible to get a 50% discount? 1. So 1 out of 10. And then times 1 out of, times 1 out of 10. I would have just written 1 out of 10 squared, and then the answer is 0.01. Okay, that multiplication rule only works as long as they are independent. If it's one of those things where you're pulling tickets from a bag and there are only 3 50% off tickets out of the whole bag of 100, the multiplication rule does not work for that because the probabilities are not independent. Okay, so still going on with this, the probability that none of the first 3 customers gets more than a 30%. So more than a 30%, how many of them are more than 30%? Just the one. 50 is the only one that's more than 30%. And we're saying none of them get more than a 30%. So how many total fit in that category? Don't get more than 30. 9. If one of them is more than 30, that means 9 of them are not. So I'm saying not more than 30, not more than 30, not more than 30. So that's 0.9 to the 3rd power. I don't expect to see how it says this first piece here, 1 minus the probability of 50%. I don't need to see that worked out. What I need to see is 0.9 to the 3rd. Okay, this is different than an at least or an at most. This is saying each individual does not get that 50%. So there are 9 other ways to do that. Now for number 5, it says what's the probability the first customer to win a 30% is the 6th customer in the store. Well, the 30%, I'm apparently really good at doing that lately. Okay, there are 2 30%, right? So what that means for this is that means my first person does not get a 30%, second doesn't, third doesn't, fourth doesn't, fifth doesn't, 6th person does. So that means in order to do this problem, I'm going to be looking at 0.8 to the 5, because that means I have 5 people not getting it, and then I get somebody that does get it, so that's the 0.2. Now, they're writing this out to redonkulous decimal points. What do we take our probabilities out to in this class? 4 decimals. So we should have done 0.0655. Okay, that means if we were to put it into percents, it would have been 6.55%. Okay? Then there's the wonderful at least problems. Even if you don't understand the reasoning behind the at least problems, you should be able to say, hey, I don't get it, but I know what I always do. What do you do for an at least problem? 1 minus the complement, 1 minus the opposite. So they're saying, what's the probability that at least one customer wins a 50? Well, I would do 1 minus nobody wins a 50. So that would be 1 minus nobody winning a 50. That's 9 out of 10. That's the probability of not getting a 50 for those first 5 customers. Okay? And all the work I would expect to see here is 1 minus 9 over 10 to the 5th, and then 0.4095. Okay? Questions on that one? I have a feeling that the at least and the at most for this entire unit are going to be the ickiest ones. But it's okay. You can do this. I wanted to give you a high five. It's like, yes. Yes. Okay. So you understand that when we're doing at least, we're always going to do 1 minus the opposite. Okay. So the opposite of winning a 50% discount is not winning. And so that's where the 9 out of 10 comes from. Okay? All right. And then for number 7, as you enter the store, 4 people all win a 50. Oh, we're on a winning streak. You're going to win a 50. What's wrong with that? Is that right? No? Why not? It's hot. We're on a hot streak. I'm going to get a 50%. Yes. Why? There's just one word. Starts with an I. Independent. Yes, they are independent. Each time, it doesn't matter what happened before. They are independent. There is actually a property. What is it? It's so funny that this is actually what it's called, but it is the forgetful property of independence. If we're talking about independence, then basically you can forget what has ever happened in the past. Do you understand? It doesn't matter. There's no such thing as a winning streak and the table is hot. So please, don't gamble. There's no such thing as a hot, slot machine. There are good poker players. There are good things that you can do, but there's no such thing as a lucky streak. Okay? Don't do it. Unless you're good at counting cards. But then don't do it because they'll beat you up. No. When I was younger, I always dreamed I'd learn how to count cards. Seriously wanted to do that. I was like obsessed with it. I'm going to count cards. There's nothing wrong with that. It's not illegal. They still don't want you doing it. There's no law out there saying you can't count cards. That's my dream. Yeah, I'm sad. Yes. Blackjack? Keep track of what cards have gone out. And counting cards is a process where it's basically you keep a running sum. And depending upon what your running sum is, it kind of helps you determine what's left in the deck. So you make better guesses. But like if you've ever seen like Bringing Down the House or read Bringing Down the House or seen what was the... Oh, they did. It's like, okay. I didn't see that in The Hangover, but there was an actual movie about the MIT students who went to Vegas and it wasn't Bringing Down the House. It was 21. Was that it? Bringing Down the House was the name of the book. 21, yeah. And they basically went to Vegas and made millions of dollars. And then the casinos caught on to what they were doing and all heck broke loose. Because it's not illegal, but they still don't. It's a private organization. They can kick you out if they don't want you there. So, which is also why if you're going to a casino and you're playing 21, they usually deal with, I think it's like 4 or 5 or 6 decks at a time to make it harder to keep track. Counting cards. Strange teacher goals. I thought it was cool. Watch 21. It's freaking awesome. Math. Probability. For those days that, no. I think it's funny. I'm thinking 21. Y'all are thinking The Hangover. I don't know if I've ever seen The Hangover. Okay. So this is where we left off. And like I told you guys, we're going to be doing a heck of a lot of problems from the textbook. So if you're one of those who are like, oh my God, I have to have the problem in front of me, bring in your textbook. Or you could write down problem number 23. We're on chapter 13. I wonder where that would be. Ah! Okay, so here we have car repairs. And we're going to do several problems that kind of deal with this situation. I want you to read through this and talk to each other about it. What do you think? What is the probability that we will need no repairs, more than one repair, some repairs? How does that work with what we're talking about here? And ladies and gentlemen, if you haven't thought about it yet, I know that there are message boards or message lists or blasts or whatever that you guys are all part of. But this is a very good unit to do study groups with. Because trust me, you want to argue through these different questions. You want to talk it through. Hey, go to Starbucks. Go to Panera. Have a study group. You would be surprised at how helpful that is. And you want to be able to get into the habit of doing things like that. Because I'm telling you right now, study groups are lifesavers in college. And if you can successfully do a study group, life will be much better. All right, in order to answer these problems, you need to first think along the lines of what category would you fall into? If I needed no repairs, seeing how we broke down this into once, twice, 3 or more. Sometimes what we like to do here is to actually draw, sometimes these are called probability models. So we'll say repairs, and we'll say probability. And so they list out once is what percent? Twice was. And 3 or more would be. So is that a correct probability model? What about 0? Because what are my probabilities all supposed to add up to? 1. Those do not add up to 1. So that means I have to tack in that other case of having no repairs. So what is the probability of not needing a repair? 72% or 0.72. A lot of times what they'll do is they'll give you a certain set of choices, and then there's another category. Sometimes it literally is just other to fill it out to 1. Yes? That's what I wanted you to think about here. If I had to take my car in to be repaired, and they're talking about 1 year period. So let's say in February I took my car in to be repaired. And then again, I went and took my car in to be repaired in October. Would you say your car needed to be repaired once, twice, 3 or more, or none? Twice. You're only going to claim one of those. Okay? You're not going to say, I went to the doctor once, and I went to the doctor twice, and I went to the doctor 3 times. You're going to say, I went to the doctor 3 times. These are considered disjoint. You're only going to fall into one group at a time. Okay? So it's not like 2 is going to cover the 1 and the 2. because 7% is actually less than 17. So that doesn't work. So probability of no repair is going to be what? 0.72. No, I don't care. That's more if you're having to round. If you have to round to 4 decimals, but you don't need to state, oh, okay, it's 0.7200. Don't do that. No more than 1 repair. So who falls under the no more than 1 repair group? 1 and 0. So what's that going to give you? Bless you. What is that? 0.89. Some repairs. What are we talking about when we say some repairs? 1, 2, or 3. So I could either add all of those up, or what else could I have done? Yeah, I usually go whatever has the least amount of work. I would have done the 1 minus. What do you get? 0.28. Okay? All right, so that's based off of 1 car. What happens if I use that same probability distribution and I'm now dealing with 2 cars? Give those a shot. Quiz next class, don't forget. Quiz. Talk it out with each other. Compare your answers. Okay. So when they're talking about neither needing a repair, what we're dealing with in that case is we're talking about 2 separate cars, and we're saying what should happen for the first car? How many repairs should it need? None. And since we're doing one event and then another event, we're multiplying, and we're saying the other car is a... How many repairs? None repairs also. So just kind of showing you how this works out. So I would have done 0.72 squared, and what does that give you? Good. Okay, there's the answer for that. I would have been happy with these numbers here, and then that. This sometimes helps you set up the idea. If I say both need a repair, how many repairs is that for the first one? .28, because we're talking about the probability of 1 or more for each of them. So that's the 0.28 squared, which gives you what? Okay. All right, now we're hitting that magic thing that everybody hates. At least 1 car. How do I handle at least 1 car? 1 minus the probability of no cars. And that's for both of them. So I'm going to do 1 minus the probability of not needing a car repaired was what? 0.72. And you could have just said 1 minus this because that work was already done. And what do you get? Good. Very nice. Now, the math that was behind this, there was something that needed to be in place in order for us to do that multiplication. What do you need in order to do that multiplication? What word is hugely important? Independence. And I have no idea if I'm spelling that right. Is it D-A-N-C-E? Is it dance or dense? But I like to do the independence. Thank you for laughing. It wasn't that funny, but okay. Do you think it's reasonable to assume that one person who owns 2 cars, the number of repairs each car needs will be independent? Yeah? Anybody say no? Yeah? Depends who's driving it. Absolutely. Some people are crummy drivers. There's one teacher who every morning, when they pull up into the back lot, runs over a curb. Every morning. It's kind of funny. I hit it again. I hit it again. I hit it again. I hit it again. Well, that's going to kind of tie in together whether or not you're going to need a repair. Or my dear sweet mother, who has MS. She has very slow reaction time. Unfortunately, that means she doesn't always hit the brakes as quickly as she should. Her car tends to need repairs. Or if you have really, really nice cars, if like you've got a Vespa, not a Vespa, really nice cars and the Vespa. If you have a Tesla and let's say, I don't know, one of those other really big expensive cars. A Beamer is not on the Tesla scale of expensive. What? Maserati. There you go. You have a Tesla and a Maserati. How careful do you think most people are going to be with those cars? Very. So, when we're talking about this independence assumption, you need to think further than just, well, yeah, of course they're independent. This car is not going to reach out and start banging on the other car and say, if I'm damaged, you're going to be damaged too. The cars don't do that. But in order to be independent does not mean that one causes the other. Independent means that there's nothing linking the two together. But the owners themselves link those cars together. Okay? Is that kind of clear statement? In order to be independent, it doesn't mean that one does not cause the other. Independent means that there's no hidden factors linking the two together to say there's an association. But when you have one family or one individual owning multiple cars, there is something that links those two together. Just like the health of you and a sibling are not necessarily independent. If one of you gets sick, that's actually going to increase the chance for the other person to get sick because you're sharing the same space. Now, you getting sick compared to somebody in Vermont getting sick, those probably are independent events. There's nothing linking those. Okay? But one owner, 2 cars, that's one owner. That links them together. So it is not reasonable necessarily for that to work. Now, maybe you've got a person who owns a Tesla and a junker. And the Tesla they take immaculate care of, and the junker they use for whatever it needs to be used for. Don't really care about that one. So maybe those are independent. Completely different approaches to those. But you've got to be careful. All right, here's a really good question. Please read through this. Remember, if you're having trouble staying awake, you're more than welcome to stand in the back of the classroom. I even have clipboards to make life easier. See if y'all can answer those too. We've actually moved to the point we're not really going to be doing investigative tasks. We're going to be doing more actual frappies. The problem with the first couple of units is that the frappies tend to cover multiple units, and you haven't had that. So as we move through now, there'll be more straight up frappies. Okay? So when we're looking at this table here, what is the probability that the person responded increased production? Don't overthink this. One person says increased production. How'd you get that? You're more than welcome to leave that as your answer. No matter what, you have to show that. I'm not kidding. You cannot skip straight to the answer and say one more time that was 0.5049. You cannot skip straight to that. You must show that piece right there. That's absolutely critical. So then what's going to be the probability that somebody responded equally important or that they had no opinion? 82, because for this one, for B, we're looking at both of those. So that way we're looking at 82 over 1012. You're welcome to write that as 41 over 1012 plus 41 over 1012, or you could just write 81 over 1012. And what is that as a decimal? Is that right? Yeah? Let's see here. Yep. Sounds good. Okay. So still looking at that same table. Now we're talking about 3 people at random. I want you guys to work through, figure out what needs to be shown for A and B, and then think together, what would you say for C and D? These are very good questions, ladies and gentlemen. I can't hint much stronger than that. All right, so for A, what did you get for A? 0.0710. Okay, good. Come on, pop up. Here we go. And I'll show you how I show work for this in a second. And for B, what is your answer for B? 0.8833. And basically, this is all I show for work on that. It's kind of tempting for the probability problems to just write down answers, but please know that each of these problems, had this been an AP question, would have been E, P, or I. An E would have shown work and a correct answer. A P is just the correct answer. It's almost like saying you only get a 50% for showing the answer. Do you understand how critical that is? Statistics is about communicating. It's about communicating not just what your answer is, but where it came from. There's a very common saying, there are 3 types of lies. Lies, damn lies, and statistics. And there are a couple of different people. Mark Twain is attributed to saying that, and somebody else, they both argue over who came up with that first. Very famous. And that's because I can get statistics to say anything I want. depending upon how I take my sample, how I work through my processes. So statistics is not just about the answer, it's almost more about the work than anything else. Now, for C, it says, what assumption did you make in computing these probabilities? What did we use? What did we need to assume? Right. Very, very good. This is a Gallup poll. Gallup polls are very well done polls. Gallup polls, who are the other ones? Pew Research, there we go. Consumer Reports. Those guys typically do things with a really good level of professionalism and care. So they're assuming, in order to do this, that the responses are, in fact, independent. And because this is a Gallup poll, that is something that is safe to assume. Yes, sir. There are a few things that I said that you want to make sure that you understand are always good. Gallup polls, Pew Research, Consumer Reports, and something that's done by what you would consider to be a reputable institution, oftentimes universities. But Cosmo, not really a reputable statistical organization. Probably not a good thing to go off of. Geek Magazine, where are you getting your data from? Okay, so you always want to put that into perspective with each other. Okay, so here we are putting together probability, data collection, random numbers. This is big, y'all. Go quick. So what I would like you all to do is I want you to read through this. You might want to take out your flip book for Unit 3. When we were talking about gathering data, what do you need to show? Because it says, describe the simulation procedure. So if that means you need to take out your flip book to say, what do I need to show that? Do it. Go for the problem. Yes, because with the AP exams, it's very difficult to separate some of the later concepts because they really do mush together. Like when we do our next unit, we're going to start drawing histograms with almost everything. Okay? Okay, work it out. Check your answers with your neighbors when you think you've got it. There are actually two different types of probability. There's something called theoretical probability, which is where we say, okay, I know that these are the different options that we have and the ones that fit what I'm looking for. We've been looking at theoretical probability. This is something called empirical probability, which is probability based off of evidence, what you've actually seen occur. So this is still probability, it's just empirical probability. And when you're doing this, it's all about making sure that you're clearly communicating the full process. So here's my answer. And each of these things include pieces that you need to make sure that you had. Using single-digit numbers from 0 to 9 to represent the numbers on each of the tags. Context. We're drawing tags here. Use a random number generator. Select 3 numbers, ignoring repeats. Okay, because it's without replacement. Record the sum. You have to tell me what it is that we are keeping track of here. I'm not keeping track of what the individual numbers are. I'm keeping track of what their sum is. We're going to do this 10 times. And we're going to make my decision, we're going to take the number of trials that we had whose sum was greater than or equal to 18. We're going to put it over 10 for our probability estimate. Okay? There was one little case right here where you had to make sure that you ignored the repeat. Amazingly enough, there were no other repeats in all of that. I recorded my sums for each of my trials, and 2 of those had sums bigger than or equal to 18. So that meant my final answer was about 2%. Questions on any of that? Key pieces here. You want to make sure that you're talking about single-digit numbers, that you have context, that you're going to say random number, somehow make sure that you understand that we're randomly selecting numbers, 3 numbers at a time, ignoring repeats, recording the sum. How many trials? What am I going to do for my answer? Okay, no extra fluff. This isn't a complete sentence type thing. You should do this, and then do this, and then do this. And when you're done, make sure that you're doing... No, whatever. Just bullet it out. You're fine. Okay, we typically like our instructions in step-by-step format. Any questions with that? How do you think you did? What did you leave out? Anybody want to tell me what they left out? If you own it, you're less likely to make that mistake in the future. Were you? Yes, thank you. Okay, the random number generator, good. Okay, so because that's part of it, the part of it is the repeat. How many times am I going to repeat this? You didn't say numbers on the tags. There's your context. Okay, so be very careful. Anybody else? Yes. The no repeats is huge. So all of these little things kind of add together. It's not a hard thing to do, but it's so darn easy to miss one of those little pieces. Okay, let's do a couple more problems, and I'll let you guys work on your own. College admissions. You're not really worried about this right now, are you? Never! Okay, this is an actual, math. This is all about thinking, explaining, and justifying. So read through this. We're not talking about Jorge's parents bribing the college to say that you were on the rowing team. Bump. Okay, so how did he arrive at the conclusion that his chances of getting into both Harvard and Stanford are going to be about 9%, or 0.9%? What did he do to get that number? He just multiplied. So he took 0.09 times 0.1. What assumption is he making in order to use that multiplication rule? That's not the assumption we're looking at. What assumption makes it so that you can multiply? It's very specific to just the probability. They're independent. In order to use that multiplication rule, it's not necessarily about what tier you're on, what you're doing. In order to say probability of A times probability of B, they have to be independent. Do you think he can do that? Do you think it makes sense to say that his acceptance into Stanford and his acceptance into Harvard should be independent of each other? No. Why not? I agree with you. You just took a 50-50 shot? Okay. Anna. Right. There's this linking factor. What is the linking factor? Jorge. He is the linking factor. If he is good enough, that's like, sounds like you're going to be down at the bottom. If you're good enough to get into Harvard, you probably have a much better chance of getting into Stanford. It's not just saying that, ooh, there's a chance. Hey, there's a 0.9% chance that I can get into both of them. No. If you're sitting there in high school and you barely graduate finishing Algebra 2 and your GPA was like a 2 point something, do you think you have the same chance of getting into Harvard as Jorge might? Maybe not. We don't know how Jorge is doing. All we're looking at is overall acceptance rate. It has nothing to do with the probability of you getting in. Do you understand how those two are different things? They actually have computer programs where you can go in and you can put in characteristics about yourself, your GPA, any advanced courses that you've taken, your SAT scores, and they will calculate your relative probability of getting into certain schools. And even your gender, your ethnic background, your parents' educational history, your parents' income. Those things play a role in whether or not you get accepted. Okay? So it is not reasonable to do what Jorge did. It's like, dude, come on. Okay, this is going to be the last question that I'm going to give you. Well, we're almost up with time, but you'll see some of the other problems. Okay? Read this one. The first two here are probably easy answers. How did he get to that 35%? He added them. Right? That's not a hard thing to figure out. He added them. Now, in order to add, to say, because when we add, we're doing the probability of A or the probability of B or the probability of C. We're adding those together. In order to use that addition rule, what has to be true? Disjoint. What's another way of saying disjoint? Mutually exclusive. That means you're not going to do more than one of those at a time. Okay, what do you think about that assumption? Not good? Why not? Is anybody going to apply to Harvard, Stanford, and Penn and get into multiple of those? Yes. Is it possible to get into just one of those? Two of those? Three of those? None of those? Probably the bigger probability there is none of them. Let's just be honest, right? I mean, yeah, you got a better chance of getting into Penn, but still. It is not reasonable to assume. So all of the probabilities that we have been working with, in order to do the addition and in order to do the multiplication, we're looking at very narrow situations. That's why this is called the basic probability. Only in really special cases can we do this. Chapter 14 is going to be more about the general rules. What rule will always work? Yep, they're a little bit more complicated, but they will work. We use these when we can. So in your notes, I believe it is the next page in your notes, you got a ton of problems. I believe it is 2 pages. Yes, it is. Okay? So there are a total of 19 questions. We are going to be working on that during Flex. We're going to be working on that the next couple of minutes. All of the answers to this are posted on Canvas. Every single one. If you can get through all of these problems without issue and their answers are matching my answers, you should be set for 100 on your quiz next class. Okay, do you understand what I'm saying? Some of your questions on your quiz pretty much come from this worksheet. So you have to do the Khan Academy assignment. But this is also something, because I'm serious, when it comes to probability rules, it's not necessarily about how well do you understand that, ooh, we add when it says or and they're disjoint. We multiply when it says and they're independent. That's easy. The knowing when and how to apply those, that's where things get very, very tricky. Now let me see this really quick. I want to see if I put... do not worry. No, I think we're all okay with these. I don't think any of those needed to be canceled out. But these are very, very good problems. So you can go ahead, start working on those, but either way, know that you have those 3 sections from the Khan Academy, and you have a quiz next class. Bring this worksheet with you to Flex. Understood? Okay. Yes.